Okay, guys, this is, well, technically the first video, I guess you would say. The first video was just an introduction. But this is the first video on when we actually roll up our sleeves and start thinking about teaching statistics. And what I'll do is I'll give you an illustration of what I do, how I approach descriptive statistics, and I think I'll follow it up with an illustration of how to perform some basic descriptive statistics with the calculator. So let's get this thing going. First of all, definitions. It's important that students understand the two branches of statistics: descriptive statistics and inferential statistics. The first kind of major thing I did in graduate school, I worked with my advisor, and I was so proud when I took my my analysis to him because I feel like I'd done a very good job. I'd written it up well, and but all I'd done was the inference. And the first thing he looks at me, kind of smiles and says, "Well, where are the descriptive statistics?" So I think it's important that you and your students understand that descriptive statistics are these graphical and numerical summary methods that we use to describe the measurements that we've collected from our sample, whereas inferential statistics is a technique that we learn. Where we take information from a sample and use it to generalize to a larger population. For example, what if we wanted to estimate the mean wait time for drive-through customers at Tim Hortons? Well, we couldn't sit there forever and just measure the times it takes for people once they get into line before they receive their order. So what we would do, we'd take a sample. Well, the goal would be to take the sample and generalize to the entire population, which would be all Tim Horton drive-through customers. But we wouldn't want to throw the baby out the bathwater here and forget to statistically describe the measurements that we've collected. So there's two things going on here: descriptive statistics, how do we describe the measurements from our sample, and inferential statistics, how do we use information from our sample to make a broader statement about our population. More definitions that your students need to be aware of. Population, that's your entire group of subjects, elements, dogs, cats, trees, whatever your measurements have been collected on. Your sample is a subset of the entire population. In statistics, we seek to get a random sample, which just ensures that every single person in your population had an equal chance of being selected into your sample. And one thing that you'll probably want to point out to your students is just how hard it is to get a random sample. Now, if you wanted a random sample of students at Shawnee State University, that may be doable, may not, depending on access to databases and so on and so forth. But if you wanted a random sample, for example, of all voters in the state of Ohio, take your students through the thought process of how you would collect a random sample. Talk about phone interviews, phone polling. Talk about polling at grocery stores. Talk about polling at that you see in malls. Talk about mailers, voluntary response polls. Talk about these things, and every single idea that comes up, other than kind of an unrealistic one, which is to put all the names in a hat and just pull out names at random. Most of the techniques for creating a sample, a random sample, are problematic. Guys, finally, a variable. This is something that I like to point out to students that just varies from subject to subject. And obviously there's going to be repetition, but you don't want a measurement collected on a group of students or group of subjects that doesn't vary. For example, what if you get information on your students first day of class, GPA, interest, car type, your favorite, whatever it may be. But then you have one question, well, who is your statistics professor? Well, guys, that doesn't vary. That's you. So that would be of no use statistically in that it's a measurement that doesn't vary. Types of data: quantitative, categorical data. Even my graduate students continue to screw this one up. Guys, get them started out on the right track here. Quantitative data are measurements that take on a true quantitative meaning. I've given you some examples there. Point out that zip code and area code, although they would be presented as a number, have no true quantitative meaning, so those would be categorical data. Categorical data is probably the easiest to identify. Gender, political party, religious affiliation, hair color, eye color, I put running shoe preference. Anything that you can, any kind of measurement that you collect that can be put into a slot, if you will. Illustration, what I'm going to do here is I'm going to teach you how to statistically describe a quantitative variable. And we're going to talk about measures of center, mean and median, measures of spread, the range, quartiles, standard deviation, and variance. And we're also going to take a look at the types of plots, histogram and box plot, that we can use to to provide graphics, if you will, of important characteristics of our data. Guys, quantitative data, motivation for center and spread statements. Most students walk into a statistics class knowing how to find the average, but they probably don't know how to find much more than that. So, to create the motivation for why we need to study center and spread, center being kind of a measurement that's typical, spread being a measurement of consistency. I start out with a very, very, very simple example. And I tell them, let's say I'm teaching a statistics class with only 3 students, and their average on the previous exam is 80. What can you tell me for sure? Now, students are going to start blurting out all sorts of stuff. They're going to tell you that all the scores can't be 80. Half the scores have to be above 80. Half the scores have to be below 80, so on and so forth. You'll hear a lot of things that aren't correct. But what I want you to motivate with your students is the following. If we look at the formula for the mean, which is just x bar, which is the notation for the mean, which is the sum of the x's divided by n, and if we insert 80 for the x and 3 for the n, cross-multiplying gives us that the sum of the scores is 240. So the thing that they can tell you for sure, for every single data set of 3 scores with a mean of 80, the sum must be equal to 240. Now, let's create some possibilities for these 3 scores. Is 80, 80, 80 a possibility? Well, it clearly is, because it adds to 240. 79, 80, 81, is that a possibility? It is, because it adds to 240. And you can see all the 4 of the possibilities that I give you add to 240. Because I'm not worried about 240. I'm worried about creating 4 possibilities that add to 240, but have different consistency levels. 80, 80, 80, completely consistent, same score. 79, 80, 81, pretty consistent. Not as consistent as 80, 80, 80, but more consistent than 70, 80, and 90. Just to be a little tricky, the final bullet I always point out, and no one said it's a 100-point test. Maybe it was a 250-point test. 2 people didn't show up. 1 person got 240 out of 250. The reason I give that is I want to give an example of 3 scores that have a lot of variability, and you can see from 0 to 240. There's a lot of difference between those 2 scores. Guys, numerical summaries. What I like to do is start out with a data set. I want a small data set because I want to make the calculations by hand. And then I want to show them how easy these calculations are to use for technology. So first of all, how far does an employee commute to work? I never tell them this, but those numbers are made up. But we'll just assume that that they weren't. Probably shouldn't have told you that, right? Certainly don't tell your students that. Make them think that you've gone out, you've like worked hours and hours to find 7 commuters. You've measured their distances that they commute, and you're sharing that data with them. All right, gang. First thing I'd want to do is run through these measurements. I would add up the scores, divide by 7, you'll get 24. The median, I would arrange these things from low to high, show the students that the middle score is 18. But what's I think most importantly here is not just the fact that they can find the scores, that they can find the measures of center and spread by hand, but they can also put into words what the scores mean. Now, something you need to point out is to students is statisticians seem to be obsessed with percent below. For example, your median is 18. It's an equivalent statement to say that approximately 50% of the scores are below 18, as it is to say approximately 50% of the scores are above 18. But we prefer to report location in terms of approximate percentage of scores below. So you'll see that I'm consistent with Q1 and Q3 in that Q1 and Q3 the quartiles are presented as percent below. Now, quartiles are probably one of the harder things for students to kind of grasp. And they're important because they lead to the 5-number summary. So what I like to do here is talk about a string analogy. So I tell students, if I had a string and I wanted to cut the string into 4 equal parts, how many cuts would I have to make? Sometimes they'll say 4, sometimes I've even heard 5. But the fact of the matter is you need to make 3 cuts. I then tell the students this is not a class on strings. This is a class on data. So imagine if we were able to arrange our data, order our data from low to high, and we wanted to cut our data into 4 equal parts. Well, it would make sense we would call those things quartiles because of the prefix. And we need to give those cuts numbers. Well, we do. We call them quartile 1, the median, and quartile 2. Now, guys, one of the most important things I think you need to point out to your students after you've established this, and this will become more clear, I guess, once we get into distribution shapes, is the median goes with quartiles and the mean goes with standard deviation. We'll find out later that in skewed distributions, the median is a more stable measure of center than is the mean. Well, quartiles are built around the median, so that's the preferred measure of spread that goes with the median. The standard deviation is calculated around the mean, as I'll illustrate here in just a second, so it goes with the mean when defining the measure of variability around the mean. So guys, when we use the median as the center, quartiles are our spread. When we define the center as the mean, then standard deviation is the preferred measure of variability. Now guys, standard deviation is a formula that makes everyone's eyes kind of roll. Students look at that, they're like, oh my gosh, I could never, ever work one of those by hand. Well, we're going to go through one illustration to prove to them that you can work it by hand. So what I like to do here is I like to create a table, and then in the first column put my data, and in the bottom line I like to put the sum. So I would probably add 12 plus 14 plus 15 and so on and so forth, and put the sum of my data at the end of the first column. The next thing I want to do in the second column is examine the sum of the deviations. The students are quite shocked here to find out that when they take each observation and subtract the mean and sum up those scores, they will always get a sum of 0. Some of your more inquisitive students will probably want to prove that. Yeah, let them go for it. That's cool stuff. Nevertheless, in the final column, I sum the deviations. I square the deviations and sum them up. And in this case, I get 12, 12. Now, it's important for students to understand that when we take measurements, there's typically some unit of measurement. Now, in this, the 12 doesn't stand for inches. I don't even know why I used inches. It stands for miles because we're looking at commuting distances. But if it was inches, when we take the sum of the deviations, we get negative 12 inches. However, when we square this, we get 144 inches squared. And I use this as an opportunity to motivate why we end up taking the square root of the sum of the deviations squared divided by the degrees of freedom to get the original unit of measurement back I'm sorry, to get the inches squared back into the original unit of measurement. So guys, if we look at the next, we'll see that the variance keeps the measurement in units squared, and the standard deviation gets the units back into the original unit because we take the square root of the sum of squares divided by n minus 1, which, well, more about that later. All right, guys, technology. We're going to have a lot of technology here. First thing I do is the graphing calculator. There's going to be a video, and then there's going to be some videos with R as well. So let's get to it. I've included something here. I'm going to play for you. So enjoy. Okay, now let's see how we put our data in a calculator and analyze the data to get the numbers that we created by hand. When you start on your calculator, there's a key right here that says stat, and tell your students to find that one pretty quickly because we're going to wear the paint off of that key. To enter data, we go to edit, and we get our list L1, L2, L3, and if we scroll on over, we'll see we have L4, L5, L6. Let me point out one thing. If we have some data that's already there, the worst thing we can do is type over the data for obvious reasons. If we currently have 50 numbers in there, we only need 20. If we type over, we have 30 left, which leads to the wrong answer, so point that out to your students. The easiest way to delete your data, all the numbers in a list without completely deleting the list, is to go up and highlight the list and go clear, enter. This is going to get rid of all the numbers there but not delete the list. Now inevitably this is going to happen. A student isn't going to listen to you, and they're going to come up there and hit delete, and it's going to take them literally, it'll completely delete the list and all. To get this back, just go to the place you want to insert the list that was deleted. Go second function insert, and then go second function L1, and hit enter, and it'll put the list back. If there were numbers in the list when it was deleted, the numbers will come back as well. So for our problem, what we want to do is first of all enter our data. So I think enter 12, hit enter. I think the second number was 14. The next number was 15. 18, 23, 35, and 51. Now something I encourage my students to always do, especially when the stakes are high, like an examination, go back up and highlight the last number that you've entered. Go back to your data set and see how many numbers that you're supposed to have. Down here we can see that this information at the bottom of the screen I'm circling says in L1 we have 7 numbers and the last number is 51. So if you look at your data set and you're supposed to have, for example, 8 numbers, well, it tells you somewhere along the way that you failed to enter a data, a measurement. So, all right, gang, we're ready to do a statistical analysis here and find some numerical summaries. So it's pretty simple. We go to Stat, and we go over to Calc, and we go to One Variable Stats. And operating systems are going to vary. This is a newer calculator, so it has the newest operating system. Oddly, I don't like it. I like the older operating system better, where One Variable Stats will just come up on the screen. I'm going to show you what you see once I execute this. But anyway, if you have an operating system like this, enter the list where the data is. Now, if you look down here above 1, 2, 3, 4, 5, and 6, if you hit your blue second function key first, you'll see you have L1, L2, L3, L4, L5, L6, which gives you access to all of your list. For now, your frequency list will remain blank. Come on and hit calculate. It will copy and paste that into the home screen and conduct the analysis. Things to point out. X bar is 24. This is your mean. On the fourth row, we have the sample standard deviation, which matches up with what we created earlier. The population standard deviation is given here. That'll probably spark the interest of some of your students. Remember, the only difference between the population standard deviation and the sample standard deviation is the denominator. In the sample standard deviation, we divide by n minus 1. In the population standard deviation, we divide by n. I would point out regularly that nowhere in our class will we use the value for the population standard deviation that's given to you on your calculator. The SX is always the one that we use. Now this arrow right here says we've got more information down at the bottom, and if you scroll to the bottom you can see that we get the 5-number summary which we got before. It doesn't provide the range, it doesn't provide the IQR, but those are simple subtraction problems, so that should be no problem for your students. Okay, guys, I'm out of here. Have a good one.